Today we're going to start talking about using the force equations to solve problems. And when I say the force equations, this is our formula sheet here from the first test. So you can see all these formulas here that we used before: definition of velocity, definition of acceleration, two of the equations two of the equations we used a lot. How the position changes in an accelerated frame, or an accelerated state. And then the relationship between how the velocity changes and acceleration and position. We had some vector equations given this setup right here. For forces, it's just so much easier. There's really just one equation. That is the main force equation right there. Sort of a subset of that is this one, where weight is related to m times g. But really, this is the main equation. Sometimes instead of F net, you might see this, where this is the Greek letter sigma. So that means sum of, or the net force. You might also see the word net in front of force. They all mean the same thing. And we'll refer back to that. So in the chapter on forces, it talks about a problem-solving method. And this is really similar to the problem-solving method we use with kinematics problems. And pretty much any physics problem. If you go up to a physicist in a cafeteria and you ask her some sort of a problem, or you tell her some sort of a scenario and you wonder how to address the scenario, she's going to start with a sketch. So drawing a careful sketch is really important. The next thing she's going to do is to identify the known and unknown quantities. So what is it that we know about the situation? What is it that we need to know? We've talked before a little bit about the system of interest. In a previous video, we practiced sketching free body diagrams. So that is sort of a continuation of the sketch, but it's a specialized sketch. It's a sketch that includes all of the forces. And typically the way to do that is to represent the object with a dot and in the center of a coordinate, an XY coordinate system, and then represent the forces as vectors that are extending in different directions. And those directions may be horizontal or vertical, so they may be along the axes, or they may be at some angle off of the axes. And remember that the axes don't have to be in the traditional up-down, left-right orientation. And we'll actually see an example of that pretty quickly here. We'll go through the problem-solving method every step except plugging in the numbers. And then we use our equation. The net force equals mass times acceleration. And typically we apply that in the x direction and in the y direction. So you can see here, oops. You can see here we've got x. Here's a specialized case. This is still F equals m times a, but this is a case where a equals 0. So this means that velocity is constant Oftentimes it's used in a statics problem. You may have heard the word statics. In a statics problem, usually there is no motion, but the important thing is that there is no acceleration. Something moving at a constant velocity is still with acceleration equals 0. And then finally, the last step here, check your answer. Is the answer reasonable? And with forces, you're still sort of in the realm where the answer is reasonable. One thing that would probably help you out is to get a sense of what is reasonable. So if I were to tell you that a person pushes with a force of 100 pounds, and you've probably seen this before, but the abbreviation for pounds, it's actually going to make it look like 1001 D. It's like 1001 Dalmatians. You'd say this is reasonable. If I say a person pushes with a force of 500 newtons, is that reasonable or not? I lost the ability to spell. Well, it turns out that 1 pound equals about 4.5 newtons. So this would be roughly 125 pounds. So if 100 pounds is reasonable, about 125 or 120 pounds would also be reasonable. So I would say that this is indeed reasonable. So kind of keep numbers in mind. This is an important thing to remember. Just like with kinematics, we remembered that the difference between meters per second and miles per hour is about a factor of 2. So 30 meters per second is a little bit over 60 miles per hour. So if a baseball pitcher throws a ball at 40 meters per second, yeah, that's pretty reasonable. So let's look at this problem right here, and I probably should have made it a little bit bigger, I apologize, but we've got a 50-kilogram skier going down the side of a 100-meter high hill angled at 30 degrees. And the question is, what is her speed at the bottom? And we're just going to set this up today. So first, let's just draw a crude drawing here. So there's our hill. There's our 30 degrees. And here's our skier going down the hill. And the hill is 100 meters high. So if we're going to look at this problem here, we need to follow the problem-solving steps. And she has a mass of 50 kilograms. So draw a sketch of the problem. We just did that. Identify knowns and unknowns. Identify the system of interest. So we know that at the top of the hill, y0 equals 100 meters, y equals 0, so at the bottom of the hill down here. We know that v at the top of the hill is equal to 0. We know v at the bottom of the hill is our target variable. We don't know the acceleration either. Doesn't matter the time of day, so t0 is equal to 0. We don't know how long it takes her to get to the bottom. So it looks like we have quite a few unknowns here. And again, we're going to set this up. So let's make a sketch. And we have a couple, and let's just say that there is friction too. So the friction So if we were to just draw our person, let's draw our person here. So this is going to be sort of an intermediate step before the free body diagram. So we're just going to isolate the skier here. So our system is the skier and skis. Oops, not the skies. So the forces acting on this person, there is the gravitational pull of the Earth on the person, so the weight. There's the contact push of the hill on the person, also called the normal force. And then there's this little frictional force here. So if I set up an axis oopsie, we've got a problem here when we do the dots. I was anticipating what I wanted to do next. So if we set up our traditional axis like this, where we've got a horizontal x-axis and a vertical y-axis, notice that only one of the forces shows up on here. And also notice that the acceleration, in this case, is partly in the x direction, partly in the y direction. It has an x and a y component. And that makes the problem solving difficult. So what we'd rather do instead is to make a coordinate system. I ran out of room here on my little drawing board, obviously not here. I want to make this line thin also. So notice we've got our axis tilted at the same angle that the hill is. So now when we draw our forces, this one's not on the axis, but this one is. And this one is as well. And the acceleration is only in the x direction. And the 30 degrees for the hill is this right here. So we actually have two components then. So we've got a y component of the w and an x component of the w. So our next step here, we represented the object with a dot. We've got the forces. I resolved the forces into the components. And then write Newton's second law in the horizontal and vertical directions. So in this case, that's a little bit different. We really want it in the x direction and the y direction. So got force in the x direction. So we're going to have F in the positive x direction minus W sub x in the negative x direction and that equals m times a in the x direction. Net force in the y direction, we've got n upward, traditional positive direction, minus the y component of w equals m ay. So notice in this case, or actually we set it up here, that a is along the x-axis, a in the y direction equals 0. The skier is not accelerating up away from the hill, nor is she accelerating down into the hill. So in this case, we can say that's equal to 0. In a future lesson, we'll learn how to relate these two equations together. So if we wanted to figure out her speed at the bottom, we would relate these two equations. Solve for a sub x, and then use kinematics equations. To find v. So for v, that's not very good prose there, but I was running out of room. All right, so let's work on a couple specific examples from our open source book. So we've got a car mired in the mud and you want to pull it out of the mud. So you might be thinking, well, why should you do this fancy method where you hook up a rope to a tree? Why don't you just pull it out directly? Well, it says here, what force would you need to exert perpendicular to the center of the rope to produce a force of 1,200 newtons? So I said that 4.5 newtons is 1 pound. So if we divide this roughly by 5, so if we divide it by 10, we get 1,200. If we divide it by 5, so that's about 2,500 pounds. That kind of makes sense because, that's about the actual weight of a car. So the question is, can you pull hard enough to pull a car out of the mud? Because it's not only the weight of the car, but it's also it's stuck in the mud. So this is a trick here in order to exert a greater amount of force. So, I'll revisit that in a little bit. So let's first off draw our axes. And this time it makes sense to have your traditional horizontal and vertical axis. And I apologize, I made the axis a little bit tilted. All right, so we've got this perpendicular force. And then we've got these tensions. So the question is, what is this little point right here? And this little point that I have at the origin is actually this point right here. So at this point right here, there's the perpendicular force. So this force is pushing on the page down. In the real diagram, maybe that's south. And then at this point here, we've got the rope pulling off in each direction. And in both cases, it's at the angle theta. So initially, it says you need to produce a force of 1,200 newtons. So that's saying that tension is equal to 1,200 newtons. Theta equals 2.00 degrees. So pretty precise here. Okay, so the problem, it says show the problem-solving steps. So we have sketched the problem. I didn't do a very good job keeping track of what I did before, so I'm just going to get rid of that. So we've drawn a sketch of the problem. We actually didn't do the knowns and the unknowns. We did the knowns here, but then we want to know what F perp is. So the one thing I haven't done yet is to resolve it into the components. So we've got T sub x which I absent-mindedly said was T sub y. And then we've got T sub y. And I'm running out of room over here, so that's also T sub y. So the next thing we do is write Newton's second law for the horizontal and the vertical directions. Let's go back to black. Back in black. Net force in the x direction is going to equal, so we've got Tx to the right, we've got Tx to the left, and that they're the same strength as each other, so they equal 0. So there's no acceleration. And actually, that's I should have mentioned that before. So you want to exert a force on here. So the assumption is, and this would be the initial assumption to make to solve the problem, is that you're pushing this point at a steady rate. So if you're pushing this point at a steady rate, this point here is not accelerating. So AX equals 0 and AY equals 0. Right, if we look at the net force in the y direction, we've got the perpendicular force, and that's downward, so we'll put a negative sign there. We've got Ty upward plus another Ty upward. So this force and this force right here. Well, Ty equals T sine theta. Oh, and by the way, this is equal to 0. So if we plug in the T sine theta, we get negative F perp plus 2 T sine theta equals 0. So that means that F perp here equals 2 T sine theta. Two times 1200 newtons times the sine of 2 degrees, and that equals 838 newtons. And if we go with our approximation here, I should have done this earlier, 838 divided by roughly 4.5. So that's about 200 pounds. And that's a reasonable amount. Before, we had 1,200. And this value here was about 2,500, 2,600 pounds. You're not going to get many people who can exert that much force, who can tug on a rope. But if you tie a rope between your car and a tree trunk, you, or certainly you and your friend, can push or pull on this rope enough And by pushing on this rope with a small force, because of this small angle here, we've got this sine of 2 degrees. Because this is such a small number, we're able to exert enough force. So we can't push with 1,200 newtons, but we can fairly easily push with 838 newtons. The trick is, though, so one thing that you have to be careful of, this means that this tree trunk here for this to work, it must be able to withstand a force of 1,200 newtons. So that's the tricky part. All right, well, it says here that real ropes stretch under such forces. So what force would need to be exerted on the car if the angle increased to 7 degrees and you still apply the force found in part A? Or you still need to apply the force, you still apply the force in part A, the F perpendicular. So let's just do a quick sketch again. And if you're watching this, this might be a good time to practice making a sketch. And here we'll just call this theta 1. So now F perp equals 838 newtons. Theta 1 equals 7 degrees. And now what is T? So we can use this formula here, F perp equals 2T sine theta, because we've got the exact same sketch. But now we need to solve for T. So T equals F perp over 2 sine theta. If we look at the units here for either one of these, force is newtons, tension is newtons, and this 2 just came from the fact that we had the 2 force terms here. It was a symmetric problem. And then sine theta, of course, has no units. And that we come up with then 3,440 newtons. So this is only about a fourth, or roughly 30% of the force we need. So that means that as the rope stretches, or the car starts getting unstuck, you have to push harder to maintain that same force. Which means F perp must increase. So this is a real-world application of forces here. You can exert a large force by pushing perpendicular to the rope at an angle. So you don't want to just directly pull the car out. And I mean, you could do the same thing. So let's say your huge pickup truck was stuck. So this represents your huge pickup truck, and it's stuck. And all you have is a little four-wheeler. So the thing that you use to bring your pump out to the irrigation canal, or you load sticks and other yard debris in. What you would do in that case is you would basically tie, and if you have some sort of a tree around, another thing you could actually do, this wouldn't work really well, if you had a stake, if you had a metal stake, like what people use to put fences in, wire fences, you could take that metal stake and pound it into the ground. So you could pound the metal stake into the ground and then tie a rope or have a chain go between them. But remember, whatever force you're exerting here, the same force exerted over here. So for example, you couldn't just have your friend hold on to this end of the rope, because she would have to be able to hold on with a force of 1,200 newtons. And if she can do that, then why doesn't she just pull the car out directly? So tie this so you don't want the person. I should have thought of having to delete all these people parts here before drawing it. You need something solid. And then you would just tie your little four-wheel drive vehicle to that point, and then just drive away. The advantage to that is, yeah, up here, the person could push with 200 pounds, but then we noticed on the next slide, if they keep that same push, the pull on the car diminishes greatly, which means that the push would have to increase by roughly a factor of 4. And you probably can't do that, but maybe your little four-wheeler could. All right, here is another problem. 2 children pull a third child on one of these saucer sleds. So you maybe had one as a kid, maybe you still have one. So we've got F1 and F2 with the angles shown. And we need to find the acceleration of the 45 kilogram sled and child system. So that's a pretty big kid, because these saucers are plastic. They can't have a greater mass than maybe a kilogram or so, 2 at the most. So that's a 47 kilogram kid. So that kid is over 100 pounds. So you might be asking yourself, why would I be pulling this kid? That kid should be sliding for themselves. Well, that's a parenting issue. We don't deal with those in this class. Although, if you do have parenting questions, I will attempt to answer them. So note that the direction of the frictional force is unspecified. So it's unspecified on this drawing, but we can actually infer it from the forces here. So the first thing we want to do, so it says the frictional force is unspecified. That's a bit misleading. We can find it by analyzing the other forces. All right, so let's just draw those a little bit bigger. All right, and then we can notice that we've got F1 X F1Y so we're going to run out of space here for this one to draw this, label this one. This is F1, I'm sorry, F2X. And this is theta 1, this is theta 2, F1 equals 10 newtons, theta 1 equals 45 degrees, F2 equals 8 newtons, theta 2 equals 30 degrees. And this is a problem from the book. One question you might ask yourself is, are these reasonable forces? So and in my opinion, these seem too small. They're about 2 pounds each. So a gallon of milk weighs more than 2 pounds. And I think it does say 2 children here. I'm guessing that children can exert a force greater than what it takes to lift a gallon of milk. But anyway, that's just an aside. So the total force here in the x direction. So this is, note we haven't even started worrying about the friction yet, because we're using this to find the friction. That's just going to equal F1x plus F2x, and F1x is 10 newtons times the cosine of 45, and F2x is 8 newtons times the cosine of 30, and that comes out to be 14 newtons. F total in the y direction is F1y minus F2y, because one of them is up, one of them is down. So F1y is 10 sine 45 degrees minus 8 sine 30 degrees. The units of that is newtons, and that equals 3.1 newtons. So F equals the square root of the x component plus the y component squared, or 14, where's my pen here, 14 newtons. And the angle, so we've got f sub x, f sub y, f, and then we have this theta here. So we know that the inverse tangent of theta equals opposite over adjacent. So opposite is the y, which is 3.1, divided by 14. Oopsie, sorry. So theta equals the inverse tangent of Fy total and I apologize for flipping. Before I had F total Y and I Fy total. Equals the inverse tangent of 3.1 divided by 14. That turns out to be 12 degrees. So there's F, and that's 12 degrees. And the 7.5 is in the opposite direction. And F is equal to 7.5 newtons. And that's that 12 degrees now below the horizontal. So one thing that we could do strategically here, I should have done this before, but let's actually, instead of using a coordinate system like this, let's use an angled coordinate system. So now we can figure out the net force. That's going to be F minus the friction, and which is, I already forgot, 14 minus 7.5. That equals 6.5 newtons. So the acceleration, which is all in the x direction, that equals net force over mass. So 6.5 newtons divided by the mass of the kid was 49 kilograms, 49.00. So sometimes this book, they make some things really precise, 4 significant digits here, but then these only have 1 significant digit. So I'm just going with 2. So 49, but we'll say that both of those are significant. So 6.5 divided by 49. That comes out to be 0.13. Did I round that right? Yeah, 0.13. So meters per second squared, and that's at an angle of 12 degrees above the positive x-axis. I hope that helped you out here. Let's just do a quick review of what we went over. So one thing to note, and this is important, we really just have one major formula for the forces. And we created some extra formulas based on that. We haven't used the weight formula yet. We created some extra formulas, but really they were all starting with this one. Talked about the problem-solving method, and we did a problem where F, the sum of the forces, equaled 0, no acceleration. And then we did one in which the sum of the forces was not equal to 0. So there was acceleration with the kid on the sled. I just did a quick sketch to set up a problem, and we'll actually revisit this problem. You can also read about a similar problem in the book. And then we did a practical application. This is a great way to get your car unstuck. Don't try to pull the car out directly, because you can only pull with a few hundred pounds of force. But if you can tie it or something, a chain, between your car and a very sturdy object, you can exert that same small force, but it will translate into a bigger force in the rope here. And then finally, we just did some resolving of vectors, forces into components, added those components up, and then determined an acceleration using Newton's second law. Thank you, and I hope you enjoyed this. I know I did.